Hi, Math 2 Enhanced. Right here, we're going to be talking about page 16 in your packet. We're going to begin talking about graphing, my favorite part of our polynomial unit. So on your packet, I want you to read the things I don't explicitly discuss. Make sure you're reading all the parts that are in our packet. But the first thing I want to talk about with our graphs is our end behavior. So end behavior is what our graph is doing on either end. So what is it doing at the very left part of our graph and the very right part of our graph? So let's take a look at this graph right here. If I look to the very right, it looks like it's going up to infinity. So notice as my x values are getting bigger and going off to infinity, my y values are also going up to infinity. But over here on the right side of my graph, as my x values are getting really, really small, going towards negative infinity, my y values are also getting really small. They're also going towards negative infinity. Kind of creates this being high on the right and then falling down towards the left. Let's look at the one next to it. This one's a little different. This one, as my x values get super small, my y values are going up to infinity. And on the left side of my graph, as my x values are getting really big, my y values are going down to negative infinity. This graph is flip-flopped. So these are the end behaviors we see when my graph has an odd degree, meaning that my highest exponent is odd. So like for instance, if I had a cubic function or a fifth degree function or even a seventh degree function, or even if I think of a linear line, my lines look something like this when I go to graph them. So this would be an odd function. Now let's see what happens when I have an even degree. An even degree would be something like an x squared function or x to the fourth or x to the sixth. And we already know from doing quadratics that both of my ends, if you will, my end behavior went the same direction with the parabola. Either they both went up or they both went down. Well, the same is true if I have an x to the fourth or x to the sixth graph. So let's take a look at this graph. In this graph, we notice both of my ends, if you will, are going towards infinity. So as my x get really, really big, my y values are also going towards positive infinity. And as my x values are getting really, really small, my y values are getting really, really big. It's going the same direction. If you look at the one next to it, both of my ends are pointed down towards negative infinity. So this would be what happens when I have an even degree function. My end behaviors are the same. So let's jump down here to the bottom and take a look at these graphs at the bottom of our page. And let's see if we can determine if it's an odd or even degree function. And when I look at the first one, my end behaviors are going in a different direction. So I'm pretty sure this is going to be an odd degree function. When we look at the next one, both my end behaviors are going up. So this is going to be an even degree function. And then finally on the last one, my end behaviors are going different directions. This is going to be an odd degree. I can go a step further than that. And my end behavior also tells me what the coefficient is on my leading term. In other words, what's my a value? I'm going to start by talking about the even functions for a moment because we know from working with parabolas, when my a was positive, my parabola pointed up. And when my a was negative, my parabola pointed down. Basically, the same thing is happening for an x to the fourth and an x to the sixth function. So for example, since both my end behaviors are pointing down, I would know that my leading coefficient is negative. That's why my graph points down. However, here, since both my end behaviors are pointing up, I know that my leading coefficient must have been positive. So going back down to my three graphs at the bottom, my even degree one, since both of my end behaviors are pointing up, I know that my leading coefficient INT, sorry about that, is positive. So how do I know when it's an odd degree and they're going different directions? Well, if we look at my odd degree function on the left, the way that it is going up to the right and falling to the left, this is the behavior of a cubic function or a fifth degree function or an x to the seventh degree function with a leading coefficient that's positive. Well, what happens when my leading coefficient becomes negative? Then my graph flips and it falls from the left down to the right. So let's jump down to my 3 blue graphs, my 2 odd degree ones. Since this is falling from the left to the right, then I know that my leading coefficient, and we'll abbreviate coefficient this time, my leading coefficient was negative. And I can tell that just from the direction of my end behavior. So over here where I am from the right falling to the left, this tells me that my leading coefficient was positive. So let's try writing my end behavior. So often we're expected to write our end behavior. What we write is as x goes towards, and this is where as x goes towards infinity, so this is getting much bigger positive numbers. So as x goes towards infinity, so as my numbers on my x-axis get more and more positive, you can see that my graph is getting more and more negative. In other words, my y values are getting much smaller. So then I say f of x is going towards negative infinity. Those are my y values. My function's values are getting really, really small, while my x values are getting very, very large. Here, this is as my x values are getting really, really small, as my x values are going towards negative infinity. So we say as x goes towards negative infinity, my function's values, now let's see what my y values are doing. Well, it looks like it's going to keep going up forever and ever and ever. So as my x values get much, much smaller, my y values are going to continue to get much, much larger. So we say my y values or my function's values are going towards positive infinity. So let's take a look at the one in the middle. This is as my x values are getting bigger, my graph is going upwards. And as my x values are getting smaller, my graph is also going upwards. My end behavior is the same on both the right and the left. So I write as x goes towards infinity, in other words, as x is getting really large, so are my function's values. And then as my x are getting really small, going to the left towards negative infinity, my function's values are still going up. They're still getting incredibly large. So now let's take a look at this one. As my x values go towards infinity, my y values are also going up towards infinity. So as my x values are getting really large, my function's values, my y values, are also getting large. As my x values go to the left and get really, really small, my y values are going down. And so I would say as my x values are getting really small, going towards negative infinity, my function's value, which are my y values, are also getting really small. This is how I would write end behavior. So the next thing I want to talk about is turning points. This is basically where my graph is turning from increasing to decreasing. So my turning points are my local maxes and mins. So for example, this is a turning point. My graph was headed down and it turns there and heads back up. And so my graph was decreasing to this minimum point right here. Then it starts increasing and now I'm to another max. And then it starts decreasing again. I get to another min and I change directions and I start increasing again until I get to another max and I start decreasing again. So in this picture, it looks like I have 1, 2, 3, 4 turning points. And we call those turning points local maxes, local mins, global maxes, and global mins. So we can have a global max, we could have a global min, and just what it sounds like, it would have to be the greatest y value, the global max for the whole function, or the smallest y value, that would be my global min. Or I can have what we call local maxes, just higher than everything around it, and I can have local mins. Again, something that's just lower than everything around it. So in this picture, if I look at my point that I put a 1 by, this would be what we call a local min. You might say, oh, I thought it was going to be global. Well, do you see over here how my function is going down towards negative infinity forever and ever? All of those values would be smaller y values than this. This is what? About negative 2.5. So this looks to be, I don't know what this point is. Let's kind of guesstimate. This looks like it might be 1.5 and 1.5x and negative 2.5y. Again, it's just an estimation. But these y values are going to get even smaller, negative 5, negative 10, negative 15. So this would just be a local min. So would 3. 3 would also be a local min. That point is smaller than everything around it. So now let's look at what I wrote 2 and 4 on. Both of those are local maxes. They are higher than all other points around them. So this could be a local max, and this could be a local max. However, neither one is going to be a global max for the entire function, because these y values, as I go to negative infinity, are just going to keep getting bigger and bigger and bigger. So all of those y values are going to be bigger than, what would this be? Maybe around 2.5. So those y values are bigger than 2.5. And so I don't have a global max there. I would just have a local max. Well, what does it look like when I do have a global? Let's look at the middle graph. In this graph, let's look for my turning points. Looks like I have a turning point down here. My graph is decreasing. My y values are going down, 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 down. Then they stop. I get to a turning point. My y values start going up, 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 up. Somewhere right in here, my y values stop increasing and I start going down again. And then they stop decreasing and I start going up again. So in this graph, I have both a local and a global min. See if you can spot where they would be. I hope you decided that this could be my local min. This point is lower than all the y values around it. And this point down here would be my global min. It is the lowest y value on the entire function. It looks like I'm at what? Maybe negative 9, or maybe that's, does it go by 2's, negative 6, negative 8, well, maybe close to negative 10 actually then. So, but that's the smallest y value on the entire graph, so it gets to be a global min. So then this point right here would be a max, and it would be a local max because there are values of y higher at my, if I look at my end behavior, because it's going up forever and ever and ever. So those are my turning points. It says a polynomial function with degree n has maximum n minus 1 turning points. It could have less. So if I look at these graphs, for example, this one has 1, 2, 3 turning points. And this is an even degree function. It would be a 4th degree function. We'll talk about that on the next page. And so it makes sense that I have 3 turning points if it's a 4th degree function. So let's talk about how many degrees our function might be, or how many zeros it might have. Next page. We are now going to talk about multiplicity and how to find our solutions and how to find the degree of our function. So when there's 2 or more of the same root, we call this multiplicity. So what you and I have been doing is we've been factoring and saying what the roots are. So up in this box, if I look at this equation, my roots would be x equals 1 and x equals 2. But x equals 2 was cubed. And so I would say that x equals 2 is a root 3 times. And if x equals 2 is a root 3 times, then it has a multiplicity of 3. Just to help that hit home, out to the side here, if this is y equals, I could write y equals, I have a 1x minus 1, but I would have 3 x minus 2's since it's cubed. Hence why x equals 1 is one of my roots, but x equals 2 is a root 3 times, and we say it has a multiplicity of 3. So we have a multiplicity at 3 at 2, 0 at that x-intercept. And 1, 0 is just a simple 0. It means it just occurs once. So fun things happen at these multiplicities. If I have an odd multiplicity, like this 2 up above, then my graph crosses at that number. It will cross straight through, for example, if it's a simple 0, meaning it has a multiplicity of 1, or a bend if it has a multiplicity of 3. And then if it has an even multiplicity, we say that it bounces. It touches the x-axis and turns around. So let's look at this next example in two different ways. Let's not look at the blue graph. Let's only look at the factored polynomial. We've been learning how to find our roots. So for f of x, list the roots for this polynomial and also list any multiplicities. Pause the video, write that down, and then come back. So how did you do? Did you say that your zeros are x equals negative 3, x equals 2 with a multiplicity of 2, and that's because this factor was squared. There's actually 2x minus 2's, so I get 2 as a root twice. And did you say x equals negative 1 with a multiplicity of 3? So we can see those in the graph. Let's take a look at our graph. I have an x-intercept at x equals negative 3, that's this guy. I have an x-intercept at x equals negative 1, that's this one. And I also have an x-intercept at x equals 2. That's this one. So let's see what's going on there. You can see at x equals negative 3, it just goes through the graph. It just goes through at negative 3. That's exactly what it talked about, going straight through up above. And then right here at negative 1, this is what we call a bend. This, you can kind of see how my graph is approaching like an upside down parabola, like an upside down half a bowl. And then when I get to negative 1, it starts to curve up. You can almost see that this is like an S, like a little bend, an upside down bowl on the left and a right side up bowl on the right. That's what we call a bend, and that happens with our multiplicities of 3, 5, 7. My bend just gets more exaggerated the more multiplicity I have. Typically, you'll just run into multiplicity of 3's. And then let's look at what happens at our 0 of 2. This is what we mean by bounce. So at 2, it had a multiplicity of 2. And when I have even multiplicity, my graph will approach the x-axis, then it touches that 0, and then it bounces back the same direction. So this end behavior doesn't surprise me. Both of my ends are going up to infinity, and if I look in front, my a is a positive 1. My a is a positive 1, so I have positive end behavior. As x goes towards infinity, so as my x get really big here on the x-axis, my y values, my function's values are also getting really big. As my x get really, really little, so as my x move to the left and get really small, my y values are still getting really large. My y values are still getting really large. Now I'd like to talk to you about the degree of my function. So when I'm looking at it in factored form, I basically look at my exponents. So this is to the first degree. So that would raise x to the first power. This is squared, so now I am at 1, 2, 3, and 3 more. This means that I have degree 6. Again, I looked at my exponents and added them up. If I multiplied this all out, so if like in our very first lesson, if we took the time to multiply all these out, which would take a very long time, I would have to do x plus 1 times itself 3 times. And then I would take that large cubic polynomial and I would multiply it times x minus 2 times itself twice. And then finally I'd have to take that x to the 5th polynomial times x plus 1 or x plus 3. Sorry, that'd be a big, huge 5 by 2 box. But anyways, when I get done with that, I would have something with an x to the 6th as my leading term. It would have a degree 6. I can count up my exponents in factored form and see the degree 6. And let's look at the graph. This is a 0 with a multiplicity of 1 because it went straight through. This is a 0 with a multiplicity of 3 because it was a bend. And this is a 0 with a multiplicity of 2 because it was a bounce. So I take my multiplicity of 1, my multiplicity of 3, my multiplicity of 2, and I add those up, and I still get to degree 6, whether I'm looking at it in factored form or I'm looking at it in graph form. So let's take a look at our final example down here at the bottom. This particular function is graphed for us, and we're asked to find a few things. So it asked me to find my roots. So let's take a look at them. Right here is a root at x equals negative 4. The graph goes straight through, so there's no multiplicity there. There's no bounce. There's no bend. Here I've got a root at x equals negative 1. Now this has a bounce, so this would have a multiplicity of 2. And then this is my y-intercept, so it's not part of my roots. My roots are my x-intercept, so we'll pass him by for now. And then it looks like I have another x-intercept at x equals 3, and it goes straight through, so no multiplicity there. So it looks like my roots are x equals negative 4, x equals 3, and x equals negative 1 with a multiplicity of 2. So write it in factored form. Well, this is just like what you and I did in the very first lesson of this unit. We're going to take our roots and we're going to write them as factors. So x equals negative 4 would give me x plus 4 as a factor. X equals positive 3 would give me x minus 3 as my factor. And x equals negative 1 would give me x plus 1 as my factor. But this one is a multiplicity of 2, so I'm going to square it. Now, thankfully, I don't have to multiply this all out. I can see what my polynomial is right there. So, and we're not asked to multiply it out, so I'm good just leaving it in factored form. My x-intercepts, I'm going to write those as coordinates. So I have one at negative 4, 0, I have one at negative 1, 0, and I have one at 3, 0. You might wonder about multiplicity there. Roots have multiplicity. Roots are my solutions to my equation. So x equals negative 1 is the solution twice. And so it's a root twice. It has a multiplicity of 2. But as far as x-intercepts go, it's just an x-intercept one time. It's just the graph touches the x-axis at the x-intercepts. So we just write it that way. My y-intercept, it looks like it's 0, negative 12. My end behavior, we always start with as x goes to, and you could say positive or negative, and then you'd say the other one. And then I say what my f of x does. So in this particular graph, both end behaviors are going up. I happen to know then it's an even degree function. I also know that my leading coefficient, is positive just from looking at my end behavior. So my function's values are going to infinity. Now turning points, I can see 3 turning points. Looks like we have one right about here. We have one here, and we have one right about here. So it looks like I have 3 turning points, and it wants me to label them. So this would just be a local max because it is definitely, there's higher y values, like over here. Everything over here is a higher y value than this little y value of 0. This would be a local min, and I say that because all of these y values over here are smaller than it. And this would be my global min, because there's no y value smaller than this, and I'm not sure what number this is. It's kind of hard for me to read this. I'm not sure if you can see it in your packet better. It's a very small copy. But that would be the lowest y value on this entire function, and so that would be my global min. No global max on this particular problem. I also want to make the connection. When I notice because of the graph it's an even degree with a leading coefficient that's positive, well, let's look. It is an even degree. It's x to the 4th, and my leading coefficient is a +1. So it kind of all comes back around together. At this point, I'm going to stop the video as far as our graphing notes. And if you'd like to go ahead and talk about the next page, then you can look at the video for page 18.